Okay, this is an antenna program that I gave a couple of years ago at a few of the clubs in the local area. Feed point impedance. The ratio of voltage to current where you connect the feed line is the feed point impedance. Impedance is simply the ratio of voltage to current. For coax-fed antennas, the ideal feed point impedance is 50 ohms. We typically use 50 ohm cable. For coax-fed antennas, I want the feed point impedance to be somewhere between 25 and 100 ohms. So when fed with 50 ohm cable, you're going to have an SWR of 2:1 or less. The feed point impedance contains resistance and usually some reactance. The resistance part is what consumes power, whether it be power as heat or radiated power. The resistance component takes into account all energy consumed, radiated and lost. We consider radiation resistance to be in series with the loss resistance. In other words, whatever the radiation resistance is, it is in series with the ohmic losses of the wire or conductor that the antenna is made up of. Now, this is mostly a concern with vertical antennas. Now, the dipole is the basic building block of almost any antennas. The dipole is a very good antenna by itself. The dipole is also used in various forms of high gain arrays. In general, I tend to use dipoles for contesting, and I tend to think that they're pretty much foolproof antenna. Now, we need to remember that any conductor or wire may be center fed with coax, center fed with open wire line, off center fed with open wire line, off center fed with a single wire. It can be end fed with open wire line, that's called a ZEP antenna, or it can be end fed with a single wire. The trick to almost any antenna is matching impedances. In general, we want to match the impedance of an antenna to the 50 ohm output of a modern transmitter. There's many ways to do this. Some are good and some are not so good. Feed line loss may be an issue, so we need to always consider feed line loss. For feed line loss, there's two losses. There's the typical feed line loss that you're going to get per foot regardless of the SWR. And then there are additional feed line losses per foot due to an SWR. In general, the lower the SWR, the lower these additional losses are going to be. Okay, let's be specific about a half-wave dipole. The impedance at the center of a half-wave dipole is near 50 ohms. Now, for 100 watts to the antenna, you will have 1.4 amps at 70 volts at the center of the antenna. Now, the impedance, which is simply the voltage to current ratio, varies with the height above the ground. Now, the reason it varies is that the antenna is going to radiate straight down and the wave will be reflected back up from the ground. So reflections from the ground passing over the antenna are going to induce currents in the antenna itself. And this is going to change the resultant current. So the impedance or voltage to current ratio is going to change. If you've got 1.4 amps in the antenna from the transmitter, and then you have the reflected wave from the ground passing over the antenna, it's going to induce current in the antenna, And depending on the phase, which is determined by the height of the wire above the ground, that current, the new current that's induced in the wire, is either going to add to or subtract from the original 1.4 amps that you started with. Now, this is a graph showing the impedance of a dipole versus the height of the dipole above ground. As you can see, the impedance starts at very low, at low heights above the ground. As the antenna is increased, the impedance is going to go up at about a quarter wave above the ground. You can see that the impedance is around 75 ohms. As the antenna goes higher than a quarter wave, the impedance reaches almost 100 ohms. As the antenna continues to go up, the impedance comes back down until you're about 72 ohms at approximately a half wave. As the antenna goes up, the impedance will go down to below 60. As the antenna continues up, the impedance will start to rise again, but it won't go as high. And the impedance will then, as the antenna continues to go up, the impedance will go down, back up, down, back up, down, back up, but it will approach 72 ohms as a limit. So the higher you go, the impedance will be oscillating around the 72 ohm point. Now, a word about radiation resistance versus loss resistance in a dipole. The radiation resistance is about 50 to 70 ohms in a dipole. Loss resistance is typically only an ohm or two. In a case where the loss is 2 ohms, we still have good efficiency. You can calculate the efficiency by taking the 50 ohms, which is the radiation resistance, and dividing it by 50 plus 2, which is the radiation resistance plus the loss, the ohmic loss. You get a factor of 0.96, and that means that your efficiency is 96%. Now, in 160 meters, the loss resistance may be 3 or 4 ohms in a wire because you've got a whole lot more wire on 160 than you would on most any other band. But still, you're going to be in the 95, 96% efficiency with almost any dipole. Now, let's take a quick look at loss at 40 meters for a half-wave dipole. We're talking about maybe a 65-foot, 67-foot half-wave dipole. And depending on the material used to make the dipole, whether it be silver, copper, brass, gold, aluminum, zinc, whatever, I've got a chart here that shows the loss resistance. And as we can see that with copper, we've got like 1.61 ohms of loss with a copper antenna. With aluminum antenna, it would be like 2 ohms. Now here we have a diagram showing the current distribution on a dipole. Remember, the dipole is fed at the center, and at each end, there's no connection at either end, and the current at either end is going to be 0. And the current is going to be a maximum at the center. Now, actually, we're showing just a curve here that doesn't move, but the actual current shown here as a positive value at the center of the antenna oscillates at whatever the frequency is from a maximum positive value to a maximum negative value at the center. Now, this slide shows the voltage and current on a half-wave antenna. We went over the current distribution, how it's always 0 at the end of the antenna or at the end of the wire. The voltage is a bit different. It is always high at the ends of the wire. The voltage at the end of a wire will oscillate at the frequency back and forth from a positive maximum value to a negative maximum value. So the voltage at the end of the wire is always going up and down between two extreme limits. At the center of the antenna, the voltage shows here is 0. Go through 0 at the center of the antenna. The impedance of a half-wave antenna is low at the center. And the impedance is simply the ratio of voltage to current. So when you have a low voltage divided by a high current, that is a small number, which is a low impedance. At the end of the antenna, you will have a high voltage divided by a very low or 0 current. That's going to give a very high impedance. You have the voltage at the end of the antenna is high, where the current is low. So the impedance at that point is still the voltage divided by the current, but here we have a high voltage divided by a very low current, and we're going to get a very high number, or a high impedance. So the impedance at the end of the half-wave dipole is going to be high. The impedance at the center is going to be low. And again, impedance is simply the ratio of voltage to current at any point on the antenna. So if we have several thousand ohms of impedance at the end of the antenna, and we have like 50 ohms at the center, as we go from the end toward the center, the impedance is going to gradually go down from several thousand through some point at which it's 300, another point it may be 100, and if you keep on going to the center of the antenna, you are at the 50 to 75 ohm point, typically for a practical half-wave antenna made of wire. Now let's talk about the feed point of a dipole. There's several things that are probably not widely understood. A dipole does not have to be fed at the center. The impedance at the center of a half-wave dipole is about 50 ohms. That makes it very simple to feed a dipole with any of your common types of coax at the center, because you have a low impedance point at the center, and coax is typically a low impedance feed line. So that all works out perfectly. The impedance at the center of a full wave dipole is going to be very high, maybe 4,000 ohms, but some high number in the thousands of ohms. And of course, the center of a full wave dipole will be at a current minimum, which means the current will be low, the voltage will be high. As a result, high voltage, low current means high impedance. So the impedance at the center of a full wave dipole is going to be very high. The impedance between the current maximum and the current minimum is going to vary from 50 to 4,000 ohms or so, depending on where you decide to attach your feed line. So 50 ohm feed line would attach at the center. An extremely high impedance feed line, such as open wire line or something like that, could attach at the end of the antenna, or it could attach near the end of the antenna, or maybe a third of the way between the end of the antenna and the center. All these are acceptable points for feeding a dipole, whether it's a half-wave dipole or a full-wave dipole. Okay, let's look at some special cases here. If we had a 135-foot center-fed dipole, that's an 80-meter dipole fed with coax in the center, and we wanted to use it on 20 meters, 14 megacycles, we would find that the center impedance of that dipole is a 4,000 ohms on the 20-meter band. So that would not be a very good match to coax. And that's one of the reasons we say you can't use a half-wave 80-meter dipole on 20 meters. You're not going to get a good match. Now, looking at this 135-foot center-fed dipole, on 20 meters, it has an impedance of 4,000 ohms. That means that there's no real good way to feed that with open wire line or coax and have a good SWR. However, there is one trick we can do. If we had a piece of 300 ohm feed line and we cut it to an odd multiple of a quarter wavelength, then we would be able to transform that 4,000 ohms down, maybe to 300 or 400 ohms, something like that. And we would be able to get a fairly close match to our 50 ohm coax. And we would probably use a balun to make the connection from the open wire line to the coax. This still wouldn't give us operation on other bands. We'd still have to use a tuner, and we'd have to evaluate whether or not the SWR on the open wire line or the coax was going to be too high and give us excessive losses. So this is not a real good way to get a multi-band antenna. Now we have the case of the 135-foot off-center fed antenna. These are typically built with one side 45 feet and the other side 90 feet. And if you do that, you still have a 135-foot dipole. But if you feed it off-center, you'll find on 20 meters, your feed point impedance goes from 4,000 at the center to about 180 ohms at the off-center point. That's a really big difference. Yeah, this is the easy neck plot showing that the off-center fed dipole has an impedance of 180 ohms at 14 megacycles or 20 meters. Now, with a 135-foot off-center fed antenna, a point can be found where the impedance is a fair match to 300 ohms on multiple bands. The SWR on an open wire ladder line is now low on all bands between 2 to 1 and 4 to 1. The loss is very small on these lines anyway, so the SWR doesn't have to be really low for negligible loss. And a 4 to 1 balun can be used to match the ladder line to the coax. Now, these are curves that show a fundamental half-wave antenna at the top. That antenna operates on its second harmonic, like a 80-meter antenna at the top, then a 40-meter antenna is the next one down. Then the third harmonic, and then the fourth harmonic. So we're looking at 3.5, 7, 3 times 3.5, and then 4 times 3.5, which is 14 or 20 meters. And we can draw diagrams like this right on up to through 15 and 20 meters if we wanted to. Now, what I've done here is I've taken those graphs or those curves, and I've drawn a line at the feed point where we would have an off-center fed antenna fed. And you would notice that the ratio of voltage to current, and the ratio of voltage to current is the impedance. The voltage to current ratio is pretty close or pretty similar in all of these curves. So we have found a point where the impedance or voltage to current ratio is pretty close to the same on 80, 40, and 20 meters. And of course, the third one down there, that's probably somewhere near the 30-meter band. Now, using my EasyNet program, I have calculated what the impedance is at this point. On 80 meters, it's 100 ohms. 40 meters, it's 140 ohms. And on 20 meters, it's 180 ohms. So we're down in the 100 to 200 range for the impedance at the feed point of an offset and fed antenna on 80, 40, and 20 meters. Now, let's look at adding a 4-to-1 transformer here, impedance transformer. If we did transform the impedances with a 4-to-1, we would find that if we had 100 ohms, a 4-to-1 will take it down to 25, and our SWR is 2. If we had 200 ohms, the 4-to-1 transform would transform that down to 50, and we'd have a perfect match. The impedance was 300 ohms. The transformation would take it down to 75 ohms. We'd have a 1.5 to 1 SWR. And at 400 ohms, we would come down to 100 ohms. We transform it down to 100 ohms with our balun, and we'd have an SWR of 2. So if the impedance is anywhere between 100 and 400 ohms, our 4-to-1 impedance transformer will bring it down to within a less than a 2-to-1 SWR. Okay, it's not really quite that easy. You've also got to be careful with the feed line length, because unless you have a 1-to-1 SWR on any feed line, doesn't matter what it is, that feed line will act like an impedance transformer. And you will get a different impedance out of the transmission line than you will at the output than you will the input. So there will be a difference in impedance. So if you have a 2-to-1 SWR, then you're going to have slightly different impedances depending on how long your feed line actually is. Now, one of the ways to, well, there's no way to get around that really. If you put the balun at the antenna, that gives you only one feed line to worry about. However, if you have a piece of 50 ohm line and you're running a 2-to-1 SWR, you are going to get some variance in the impedance looking into that 50 ohm coax. Probably going to be minor in most cases, but that's still another factor that you have to consider. Feed lines act as transformers. Okay, so now we're looking at the OCF, offset and fed antenna on 20 meters with an impedance of 180 ohms at the antenna. The 300 ohm line SWR is about 1.6. The impedance looking into that 300 ohm line will vary depending on the line length. If the line length is close to a half wavelength long on 20 meters, then you will end up with an impedance of 180 ohms. And a 4-to-1 balun will give you 45 ohms and almost a perfect match to a 50 ohm coax with an SWR of 1.1 to 1. So that's the conditions in which an OCF will work on 20 meters. Okay, what about 40 meters? Well, with an impedance of 140 ohms at the antenna, using that same half wave on 20 feed line, that 20 meter half wave is now a quarter wave long on 40. And this transforms the 140 ohm antenna to 640 ohms at the input of the ladder line. And adding a 4-to-1 balun is going to give you 160 ohms. And you'll end up with an SWR of 3.2. Now, that's not so good. But if you change the feed line length, the open wire line length, you'll find that with an impedance of 140 at the antenna and a half wave line on 40, the input impedance becomes not 640, but it becomes 140. Now, nothing changes on 20 meters because the line is simply 2 half waves long instead of 1 half wavelength long. So now, adding the 4-to-1 balun will bring the impedance to 35 ohms. Resulting coax SWR is 1.4. So the length of that open wire line from the antenna to the transition to 50 ohm coax is really very critical. We have to make sure that it works not only on 20 meters, but it also works on 40 meters and as many bands as we can make it happen on. Now, what we find here is that some feed line lengths may not work. I guess I'm going to say most feed line lengths will not work. You have to choose your feed line length very wisely. Unequal current in each wire. So you have unbalanced currents in this particular antenna. This is not a balanced antenna. So when we try to go with a balun to go from balanced to unbalanced, we're really not going from balanced to unbalanced. We're unbalanced to start with. Also, the balun may overheat. It may have excessive losses. There's lots of things that can go wrong with trying to build an antenna like this. Now, we have had some successful off-center fed antennas, and we use them at field day. There's a good number of designs for them, and I guess what I'm trying to say is you need to be careful because copying one antenna, you may not be copying it exactly, and you're definitely not going to be putting it up in exactly the same location and probably not even the same height above the ground. And all of these things affect the impedances, and it can get very complicated very fast. Now, I have an alternative to the off-center fed antenna. Actually, it's a alternative to multiband antennas in general. And what I do is try to build multi-wire dipoles. Multi-wire dipoles from multibands. You can put 2 or more simple dipoles, connect them to the same single feed line, and you can get multiband operation. It works good. It minimizes the number of feed lines to the shack, and it minimizes antenna switching, particularly in a contest, which is what I'm interested in. This is a picture of a multiband dipole I built for 40, 20, and 10 meters. There's 3 elements there, 3 separate dipoles on 1 coax. Here's one I built for 15 and 12 meters. That's a 2-band dipole, 2 dipoles on 1 feed line. Now, how well do they work? Well, I've had pretty good luck with multiband or multi-wire dipoles. In 2010, I worked 100 countries on 40, 20, and 15 meters. This is in one weekend. 2011, I worked, I was good enough for a number 2 single op in Virginia. 1,323 QSOs, DX QSOs. 2011, I worked 100 countries on 20 and 10 meters, and I only worked 96 on 15 meters. 2011, I made 1,474 QSOs, and I worked 100 countries on 4 bands, 40, 20, 15, and 10 meters. So I think the proof is there that these antennas work. There is some interaction between any antenna and any wire that's nearby. So you've got to be careful where you put your antennas up. If you've got 2 antennas in your backyard, they're going to have some interaction. Sometimes the effect may be good, sometimes it may be bad, and sometimes there may be no effect at all. You'll have a more pronounced effect if a nearby conductor is a resonant length. Now, what we're interested in here is, how do you make your antenna work? Well, there's more to it than just that. You need to listen a lot. You need to learn about radio wave propagation. You need to know when to get on. You can use the ARRL propagation tables to guide you in that. You can use the propagation predictions in your logging software. I use DX Lab suite of programs, and that has some propagation prediction. And you can learn how to time your calls by listening. Basically, you can make almost anything work if you learn the fundamentals, pay attention to details, and you experiment with different antennas. And most of all, have fun.